right.
All right.
I appreciate you checking. Yeah, absolutely.
In the homework, I've put up the homework problems that you'll see from the book.
This is the actual homework? Or these are examples?
No, this is the actual homework.
Okay.
I'm just kind of showing you. You get the sheet, the word sheet off of Blackboard. I'm going to write some notes about the homework problems specifically. So you're at 11.2 in the homework. We did an example with the example we did in class was 11.1 with jacks. So we covered that. You've got 11.3. There's, to solve 11.3, you're determining sample size. There's, in last week's notes, I don't want to go over the equation for the sake of time and because it's well covered in the notes. In the inference notes from last week, there's an equation on the last page that we didn't get to. In fact, the equation is n equals, make sure I got it right. I don't like the way the book explains it. So last week's inference notes, you'll see on the back page how to determine a sample size in. It's use the equation 1.96 times the standard deviation over the amount of error you want, and then square it. And the notes, it's on the very last page. So, and the answer's in the back of the book too for that problem, so you can check your work. But in 11.3, you just need to fill in the numbers and solve for n in that equation.
What's that?
This one?
Yes.
S is
the
S? Standard deviation.
And that's everything squared?
Everything squared. So you're gonna in the problem you're given the standard deviation, and you're given the amount of error to tolerate. In fact, in 11.3, you actually they say the estimate is within 200 of the mean, so that's your error. And assume that a preliminary survey estimates that the last year's mean was 35,000 with the 1,000 standard deviation. So there's your S. So now you've got all the information you need just to do the math correctly, and now determine your sample size. So they told you they want you to tolerate $200 in error and use a standard deviation of 1,000. Question? 11.7 is a lot like 11.1, but basically use one of three methods of t-testing that we had in 11.7 to determine if their hypothesis is supported or not. They resemble problems like last week. They had a sample of 75 students. They give you a sample average, and standard deviation is that sample different than the comparison figure. So use one of the three ways to test. And then you have 11.10. They give you information, present a a hypothesis and a null hypothesis and then evaluate them. So you have to state a null and a research hypothesis, and then use one of the three methods for a t-test. So nothing, we've covered all that. Is everybody okay with 11.3, just solving for that equation? We'll explain it more in class next week.
That's 15.1.
For
That's supposed to be 11, 15.
it's 15.1 is a separate problem.
So we, for 11.3, we have all the, we just got to apply the formula.
Yeah.
I see.
Essentially,
I'm reading
it's-
it now.
Yeah.
Yeah.
Just put 1,000 in for S and 200 over E, so, and then just solve it. And we'll go over it in more detail next week. Let's hold off on this one, so I'll put a star by it. We're going to go over that. You've got total of 4 SPSS problems. The first one is you're using the training data set and you're determining whether the turnout times for trained versus untrained units are statistically different. So there's a video on how to do t-test in SPSS. So video and t-test in the lectures. And then in the second SPSS problem, it's the same video. This time you're testing whether or not having a supervisor at the station decreases turnout times or not. So in the video, I think the video uses response time, so just substitute turnout time.
Yes.
And that leaves 3 types of problems we haven't seen. Okay, so there's a video on how to do t-tests for the first 2 SPSS problems, and it says do an independent samples t-test. So the video covers that. Problems 3, the last 2 problems I numbered it out of sequence. And I've got 2 number 5s, but the last 2 SPSS problems, there's a video on how to do chi-square in SPSS. So you'll run a chi-square test using a different data set, neighborhood association. And that gets us into what's the difference between t-tests and a chi-square test. So we've been doing t-tests with that when we calculated the range of 95% confidence, and then drew a t-distribution and came up with a t-critical and t-obtained. Those were all t-tests. If you notice, or if you remember from the turnout time variable that you'll be testing in your first SPSS problem, you were looking at turnout times for trained units and comparing them, so versus turnout times for untrained units. So some units had undergone training, some units had not engaged in training. The dependent variable here would be what? The turnout times. Right. So we're looking at, did the program work? That means the independent variable is training or trained or not. Question mark. Essentially, you're looking at, does the training work? Does the training have a significant effect on turnout times? Turnout times is measured in seconds, so it is conducted at what level of measurement? Interval. T-tests can only be done on interval. Okay. If your dependent variable is at the interval level, you can run t-tests. In the example that we had before, oh, sorry.
Yeah,
Oh, you can read
yeah,
I was
No, but
right
erase that,
underneath
right?
that.
Was this okay to erase that?
Yes,
Okay.
I was underneath that.
Okay.
Is that independent variable? Is that trained with question mark?
Yeah, it's a
Okay,
question mark.
got it. Okay.
So you're determining if the training program worked. You're comparing untrained versus trained units on their turnout times. And dependent variables at the interval level because it's in seconds. Before the break, we were looking at automobile cost in dollars between the city mechanics versus Jack's Auto. What's important is to identify, excuse me, the dependent variable in this case, which would be the cost in dollars. That's an interval level measure. Independent variable is less important, but you're determining if switching over basically to private contractor versus public, Jack versus city work. So it's interval, so we did t-test. With the cows from the homework, adding corn oil to the feed, what were we looking at as the dependent variable?
Wait.
Weight, which is in pounds, which is an interval level measure. So, interval level dependent variable t-test. And you'll, for the first two SPSS problems, you're looking at turnout times, and I tell you, run an independent samples t-test. Sometimes your research question may have a dependent variable that's not interval. Voted or not. Okay. Could be voted. Yes, no. You might want to determine the independent variables that determine party ideology. Dem, Republican, other.
But on those you can't run a t-test.
No, you cannot. And that's why you cannot, for the last two SPSS problems, you're not going to be doing a t-test. The question says run the appropriate statistical test. The appropriate statistical test is going to be a chi-square. These dependent variables are measured at what level? Nominal. Categorical or nominal?
Yes, no.
So, your independent variable in a chi-square test will also be nominal. Think of trained versus untrained, or corn oil versus no corn oil, or Jacks versus not Jacks. With all the t-tests, our independent variables were nominal, and that's fine. The key determinant of what test you use is the dependent variable. In our previous examples with the t-test, they were all interval. Now we move into the world where your dependent variable is nominal. A yes, no, or you fall into some sort of category. Okay. With these, with chi-square, both your dependent and your independent variables will be at the nominal level. Questions about when to use. The determinant is your dependent variable. If it's interval, you can use t-test. If it's nominal, you're going to need to do a chi-square. The other stipulation with chi-square is that also the independent variable is also nominal. So,
Dr. Schiller, can I
Yeah.
interrupt you about 30
Yeah.
seconds? I think there's an ID card left in one of these computers over here.
Well, Fogel just came and grabbed
Yeah,
one.
one guy just came and got his.
Did he?
No, it was a female, so she just texted me and asked me if it was in here.
Yeah, Fogel just came and grabbed one. I think it was it
Yeah.
Yeah, Fogel
Okay.
grabbed
You got it?
All right.
Okay.
Thanks.
Okay, so if you look, say at page 1, suppose we want to know participation levels by race, and to determine if participation levels differ by race. Race in this, black, white, and participation is high and low. Those are the categories. We want to know the effect of race on participation. If race is only measured black-white, participation high-low. So the independent variable is race, black versus white, nominal. Participation is what we're seeking to explain. That's our dependent variable. It's nominal. High-low. If you threw in medium, I guess you could claim it's ordinal, but for all intents and purposes, high-low is a nominal measure. So because the dependent variable is nominal, we know we cannot use a t-test. We use a chi-square. Double check that your independent variable is also nominal. It is. Suppose the data, say you surveyed people and you came up with the data, race, and then high-low participation, and you see the table presented to you with the raw data. I think some students that do the survey for capstone used some chi-squares last year, so it might come in handy.
Dr. Shelley, did you say if the independent variable is nominal, then you will use the chi-square?
If and only if the dependent variable is also
Only
nominal.
the dependent.
Dependent variable will tell you what test to use as chi-squared. The other stipulation is that chi-squared, you need your independent variable also has to be nominal. But first look at your dependent variable, you see it's nominal, you know that it's most likely chi-square. If also the independent's nominal, then definitely chi-square. That's the other check. So both, essentially just both have to be nominal. Independent and dependent have to be nominal. If you look how the table is ordered, high, low, black, white. Our rows, and this is also important, are the categories of your dependent variable. So your rows is going to be dependent variable, it's participation. Your columns is your independent variable. And that's important for SPSS when you run it. It will ask you which variable to put in the rows, which variable to put in the column. Most tables should be set up similar to this, with the rows being, the dependent variable and the columns being the independent. The raw data has 35, 15 for black, for white, 30 high participating, 20 low participating. This is essentially a 2x2 table. There are two substantive rows, high-low, two substantive columns, black-white. So there's only two categories of each. And the other information that they throw in for you is a columns total and a row. Row totals, and column totals.
Dr. Shell,
Yeah.
I should know this, but 2x2, so which one is first? So if it was three rows into, it's a 3x2?
Yeah, I'd say, dependent variable first. 3 rows by 2
It
columns.
doesn't matter really.
Yeah, it's
Okay.
not really. You could say 3x2 or 2x3, and you end up, you're going to do the same thing statistically. So the row totals, we got 65 high participators, we've got 35 low participators. $50 black, 50 white. For a sample total of 100. The total, bottom right, that is going to be your N sample size. Questions on how to read the table, how it's set up. What to note is that it's a 2x2 table. We're going to introduce terms called row and column marginals. This 35 is a row marginal for the low row. The 65 is a row marginal for the high row. Each of these 50s are separately a column marginal. Which will become important in a second. There'll be a few new notations, but we see the dependent variable, independent variable are both nominal. Have to use chi-square. What is chi-square going to do? It's going to tell us if there's a statistically significant difference between black and white individuals on levels of participation. So does race affect participation is what we're going to test. The null hypothesis is no difference in participation by race, or no difference in the dependent variable by your independent variable. The categories statistically are no different than each other. And your research hypothesis, you can, before you collect this data, you should stipulate a hypothesis. You shouldn't let the data drive your hypothesis. You should do the hypothesis first, then collect the data. So you could have a hypothesis that race matters. If you want to be super specific, you could say I hypothesize that one race participates at higher or lower rates. But the null hypothesis in a chi-squares, there's no difference between the categories of the independent variable on the dependent variable. The chi-square by hand is very involved, and that's why we're going to do this example, and then the one in homework can be done for the SPSS. It just cranks it out for you in the software. So the only one that you have to do by hand is 15.1 in the homework. We're going to solve this one and then do 15.1 and then be done. And I'll let you do the chi-square with in SPSS with the videos. The chi-square statistic to calculate. And keep this table handy. Reproduce it smaller. High, low. Oh.
20, 50, 65, 35.
That's for reference. The chi-square equation, basically you're going to calculate a chi-square statistic and determine if it meets the chi-square critical value or threshold for statistical significance. The chi-square statistic tells you to sum everything at the end, and what you do in the numerator is you're going to take an observed frequency, subtract an expected frequency, square it, and then divide by an expected frequency. Each of these substantive cells, 35, 30, 15, 20, and so nothing involving the totals. Each of these, in the sense 2 by 2, 35, 30, 15, 20, those substantive cells are an observed value or FO or an observed frequency. So 35 is an FO, 30 is an FO, 15 is an observed, 20 is observed. Essentially what happened was you surveyed people and you observed this data. And these are your observed frequencies. Remember that the null hypothesis is no difference in participation by race. That's the null. These expected values, FE, that we'll calculate are what values should we expect to see in these cells if there's no difference between black-white on participation levels. And so you're going to have an expected value that will calculate for each of these cells if there's no difference in race. So what should we see in this table if there's no effect of race?
25 and 25 for each.
No, because it will depend upon your totals. This one I think works out to kind of a nice number in each, but it depends upon the totals, because if you sample more whites, if they're oversampled, that's going to affect what you expect to see, because if you oversample whites, you're obviously going to expect more numbers than black. So basically we need to calculate expected values that we should see in this table if there's no effect of race. So for each substantive cell, you've got to calculate an expected value And that is you take the cell's row marginal, multiply it by the column marginal, and then divide by n, or your sample size. Remember, this 50 is a column marginal. This 50 is a column marginal. 65 is a row marginal. This 35 is a row marginal. It's a total in a row. And that 100 is your in. It is a long process, and so we're going to do both by what you see what the computer's telling you to do and what it's calculating and comparing. So we have all of our observed values based upon the survey that we took of a sample of n of 100. Now we have to calculate for each substantive cell what should we see if there's no difference between race on participation. So if you start in the northwest cell and go clockwise, so for the black high participators, we saw 35. What should we see if there's no effect? Okay, for that cell, you take its row marginal. So we'll go northwest cell. You take the row marginal, which is 65, times its column marginal for that cell, which is 50. Let's see where we got those two numbers. We're dealing with this cell, the northwest cell. Its row marginal is 65, column marginal 50. We divide by 100. 35. Oops. 65 times 50.
32.5.
Divided by 100. Oops. Is that right? Yeah. So, if there was no difference between races on participation, we should see 32.5 in that cell. So that's our expected for the northwest cell, black high. Going clockwise to the northeast cell for white high participators, it's going to come out nice and clean. It won't always be the case, but its row marginal is 65 for the white high cell. Its column marginal is this 50. So 65 times 50 over an n of 100. That's 32.5. And these numbers of 32.5 for black and white are the same because the column marginal is the sample. You sampled 50 of each race. If I changed the numbers to 60, 50, they wouldn't be nice and clean, same numbers. So it depends upon your numbers that you sampled. Go clockwise to southeast. We're looking at white low participators. We should expect to see its row marginal of 35 times its column for that cell. Margin is 50 over 100. We should see 17.5 in here. And then when you go to finish out going clockwise to the southwest for black low, same. Row marginal is that 35. It's a different column marginal, but it's same numerically at 50. 17.5.
I got a question, just
Yes.
for the sake of argument, so.
Yeah.
You start off with the 35, I mean, in that block,
Yes.
but then the 65 is
It's row marginal.
real marginal.
Yes.
And then where you get the 50 from? So you jump
Column
from,
marginal.
Column marginal.
so the first column that okay,
Find that cell, find its row marginal,
and then find its total.
find its total column marginal.
Okay.
Yeah.
Alright.
And they both just are 50 because both
Right.
column marginals are the same.
Type shows.
Mhm.
So is that always the order to northwest?
No, doesn't matter. It's just this, I just went northwest clockwise for ease of,
Okay.
the order will not matter.
The only
But you
thing that
can,
does-
I'm sorry, go ahead.
The only thing that does matter is row marginal and your column marginal.
Yeah, I mean, you can start down here at the southwest and flip-flop do an X or go counterclockwise from there. It's still going to be the same. Yeah, you're still going to get the same number. Okay. So, for example, with whites, we observed 30 high participating whites. If there was no effect of race on participation, we should see, instead of 30, 32.5. For whites that are low participators, we saw 20. If there's no effect of race on participation, we should see 17.5. Same thing for black. Now, you can calculate chi-square statistic. Very similar in the end analysis as the t-scores. For each cell, you engage in this equation and then add up the sum. So start at just this for ease back at the northwest. Fill in the equations. We observed 35 minus we expected 32.5 over 32.5 and then square it. So observed minus expected divided by expected. Observed minus expected over expected. One correction. Square the top, not the final product. Square that. Make sure you correct that. Put the squaring at the top one. So, observed minus expected squared over the expected. So, everybody note that correction. So you're going to take, let's see, 35 minus 32.5 is 2.5. We're going to square it and then divide by 32.5. So 2.5 squared is 6.25. We're going to divide that by the 32.5 to get 0.19. Everybody see that? Square the numerator. Don't do the squaring at the end. So we got a value of 0.19. Go to clockwise to the northeast. We observed 30 minus, we expected 32.5. Square it. Divide by 32.5, the expected. And you're going to end up with the same thing. Negative 2.5 squared over 32.5 is 6.25 over 32.5 to get 0.19. And let's see how we got 0.19 for the northeast cell. If you go southeast, continuing clockwise, we observed 20. We expected 17.5, so 20 minus 17.5. Square it, and then divide by the expected of 17.5 for that cell. And you get a 2.5 squared over 17.5. 6.25 over 17.5. 0.36. The last cell, clockwise, is the southwest cell. We observed 15 minus the expected of 17.5. Square it, and then divide by the expected of 17.5. So you get a negative 2.5 squared on the top, divided by 17.5. And so you eventually get 6.25 over 17.5, which, just like before, is the same at 0.36. Does everybody see how we got these four numbers for each cell, respectively? The last thing you got to do is the summation sign. So add them all up. Add them all up. And the summation is 0.19 plus 0.19 plus 0.36 plus 0.36. The summation is your chi-square statistic, or your chi-squared obtained from your data, is 1.10. You know if I'm going too fast. So that's a chi-squared that you obtained was 1.1. What does it mean? Okay, so we started off with the observed values, and we calculate what we should see if there's no difference in race participation, the expected. They differ in each case by 2.5. So essentially, are these differences statistically significant? We calculated a chi-squared of 1.1. Is this statistically significant? Well, you've got a table you have to go to. And that table is table 4 on page 453. Okay, everybody see that?
This is a chi-square distribution.
Yep, exactly. Star or highlight, in this case they actually did get the table good for a two-tailed test. Go ahead and do the excuse me, let me double check, make sure they did it, if they changed from a different edition. I don't think they did. No, they didn't change it. Highlight the 0.05 column, or star it. For some reason, that is the 95% statistically significant column. So you're going to be looking at one of those numbers in that column. Which number depends upon the degrees of freedom. Your notes point out that the degrees of freedom are different with the chi-square distribution. It's not n-1 this time. It's the number of rows minus 1 multiplied by the number of columns minus 1. These are substantive rows and columns. Remember we said we had a 2x2 table. Yeah, the totals do not count. We have 2 substantive rows, high, low, 2 substantive columns, black, white. So 2 rows minus 1 times 2 columns minus 1. 1 times 1. 1 degree of freedom. More often than not, you're going to be dealing with 1 degree of freedom. You can have a 5x5 table, and you can do all the math. It's a pain. Computer does much better.
3.84.
3.84 is the critical value. That's our chi-squared critical.
There's number of rows minus.
Number of rows minus 1.
Okay.
Multiplied number of columns minus 1. For the homework, which we're getting ready to do the problem before you go, so you can get the full credit, it's a 2x2 table. You get into multiple 3x3, 4x5, 6x6. You can do it, but it's not. You let the computer do it. So for all intents and purposes, for the chi-square distribution, 3.84 is going to be your critical value for a 2x2 table and for the problem that you'll do by hand, which we'll do in a second. So chi-squared critical is 3.84. Remember that the null is of no difference in participation by race. Okay? It's independent. For statistical significance at the 95% confidence level, for us to say that yes, there is a difference between black and white on participation, your obtained, just like the t-scores, has to meet or exceed the critical.
Say that again, please.
So for a for the differences for the independent variable to affect the dependent variable, in this case for race to affect participation,
The obtained has to be higher than critical.
obtained has to be higher than your critical. It is not higher. 1.1 does not exceed 3.84. So you cannot be 95% confident that participation differs by race.
That's always, not just for this.
It's always right. And so basically you cannot reject the null, okay, or the null is supported. The null says there's no difference in participation by race. If we support that, well, null is supported, and therefore we cannot be 95% confident that participation differs by race, that race affects participation.
How do we know that?
Because 1.1, the obtained chi-square that we did all the math, does
Right.
not exceed that critical value of 3.84.
Okay, doesn't exceed the critical.
Yeah, that's our threshold for statistical significance at 95%. For us to say that yes, race does differ, you need to have that 3.84. Okay. Okay, let's do the one from the homework so you have the answer. And you can just turn it on over. So this is a case, not statistical significance. In 15.1, this week and next week are probably the longest of the 2 weeks. And you get week 6 off. 7 and 8 are relatively short. So 15.1, the mayor wants to know whether the city's non-whites feel that the police are doing a good job. In comparison to whites' evaluations, this information will tell the police whether they have a community relations problem in the non-white community. A survey reveals the data in the accompanying table. What can you tell the mayor? All right. So, the data show police not good job, and then police good, and it's non-white versus white. It's another 2x2 table. So our critical value is going to be 3.84. So I'm going to put this out here. Chi-square critical is 3.84. And our observed numbers that we see, 76 non-white say police do not do a good job versus 74 non-white that say police do a good job. 73 white says police are no good. 223 whites say police are doing a good job. For row totals of 149, 297, column totals of 150 and 296, and then a total in of 446. So for the homework, just copy. Even if you're doing it now on a separate sheet of paper, just attach it. And then it'll be the, I guess, what is it, 6 points? Yeah. Okay, so to get the expected values, row marginal times column marginal over n. So these are the numbers we observed. Now we need to calculate the expected. So let's go to Northwest. Starting first, non-white police not doing a good job. The row marginals and the column marginals. So for the Northwest, the row marginal is 149. Its column marginal is 150 over the N of 446. There's your N. This is a column marginal, row marginal, row marginal. $149, so that is $150 divided by 446. Let's do it for the sake of calculations. Let's just round it to the whole number. So 50. And you won't be doing any of these on homework. This is the only one by hand. So our expected in the Northwest was 50. We observed 76. Expected 50. when you go northeast to whites that say police are not doing a good job, row marginal is 149, column marginal is 296, so 149 times 296 over 446. Rounded, yep, 99. So we should see in this cell 99. Going clockwise to the southeast, whites, please do a good job. Row marginal is 297. Column marginal is 296, so multiply those two together. Divide by the n of 446. And rounding, I get 197. For the southeast. 297 times 296 divided by 197. So the observed there is 190, or the expected is 197. Southwest, row marginal is 297, column marginal is 150. Divide by the n of 446, so 297 times 150 over 446. Rounded to the nearest, yep, whole number is 100. And that's the expected that we should see in that cell. Everybody see how we filled in the table? We've already had the observed. We calculate the expecteds. Yeah.
Once we have the south, what east,
Yes.
197, do we not subtract that from 197, or 297, and get the 100?
Let's see.
Don't.
You could, but that's just a little bit more complicated way of thinking. But yeah, because 76 and 73 is 149, 50 and 99 is 149. So yeah, they should, 100 and along with the columns too, 50 and 100. Yeah, that's the. All right. Questions before we calculate the chi-square obtained? We have everything we need. So I'll go back to the northwest. We observed 76 minus the expected of 50 squared over the expected of 50. So that's 26 squared over 50. Which is 676 over 50. $13.52. Remember, at the end, we're going to sum up all these. 13.52 is already greater than our critical at 3.84. So you know there's a statistically significant relationship. But to continue it out the northeast cell, we observed 73, expected 99, square it, and then divide by the expected of 99. I give 26 squared over 99. It is 676 over 99. That's 6.83. southeast cell, we observe 223 minus the expected of 197 squared over the expected of 197. So that's another 26 squared over 197. So 676 over 197. 3.43. And then the southwest, observe 74 minus the expected of 100 squared over the expected of 100 is a negative 26 squared over 100, which is 676 over 100, which is 6.76. Questions how we get each of these numbers? Last step, add them all up to get your chi-square obtained. So 13.52 plus 6.83 plus 3.43 plus 6.76 plus 6.83 plus 3.43 6 30.54. That's your chi-square obtained is 30.54. We only needed the chi-square to be 3.84 or obtained. It obviously surpasses the critical value of 3.84. So yes, you can be 95% confident that opinion of police differs by race. So no, there's a statistically significant relationship between race and their feelings towards police. Because your chi-square obtained of 30.54 exceeds 3.84. Questions? Sorry that it took right to 8.
Here's our fault.
The copy.
Making copies.
And this is basically what you need to know. And just copy it for the homework. In SPSS, the computer will do it for you. All you got to determine is if the independent variable is statistically significant with the dependent variable. In this case, it was opinion of race is opinion of police is affected by race. Next week we'll say exactly how, but for now you know there's a statistically significant relationship between race and their opinions on police. The direction of that relationship we'll cover next week, along with the turnout, the chi-square that you need to do for the homeowners association data set, where there's a video. Questions? A lot of material. Next week's probably the last long week of involvement, and then it tails off. No questions. I'll be here for office hours on Wednesday. So you at least got 6 points. You just transfer it.
What was the null statement?
The
Did
null,
we even create one?
we didn't.
Okay.
The null is no difference between races.
I put no difference of opinions by race, and then my hypothesis is that there is a difference in opinion by
Yeah, and so then your hypothesis would be supported that yes, there is a difference by race.
So that was 15.1.